In 3.4, we're going to be looking at characteristics of rational functions. And so we're going to kind of be taking a step back, looking at some of the parent functions that we already dealt with in Unit 1, and kind of look at how we can dive in and grab some of those characteristics, not by just looking at the graph, but considering what the equation looks like. So just kind of start out, remember these are two of your parent functions. These are rational functions, meaning they can be written as a fraction. You can notice some similarities between the two. It looks like there's this imaginary line in here, both vertical and horizontal, that these functions are never touching. Same thing here. Looks like there's these imaginary lines, things aren't touching. And we're going to dive deeper into that. Before we can kind of move forward, though, is we need to note some notation, some new notation, and some new notation from this chapter. The first two pieces here and this one down here are kind of going to be new for this section. And this is x as it approaches a from the left, and x as it approaches a from the right. This is just instructions of how to read the notation. It is not a negative, like making the a negative or making the a positive. It is not a multiplier or an exponent. It is just an instructions of saying as x approaches a from the left, meaning coming from the left of the graph, what is it doing? Coming from the right of the graph, what is it doing? These dealt with our end behavior as x approaches infinity, negative infinity, as our function approaches infinity, and negative infinity. And we looked at all of these when we were looking at end behavior earlier in this unit. And then last one, f of x approaches a. This just means the output approaching a. And so if you do have further math classes to take after college algebra, you'll see a little bit more of these notations. But again, I just want to kind of emphasize these, and we'll understand them a little bit more as we move forward. So let's first look at these definitions here, and then we'll kind of jump back up to what we're looking at here. So two new vocabularies or things we're going to look at is something known as our vertical asymptotes. A vertical asymptote is a vertical line, x equals a. This is an equation for a vertical line we've looked at before, where the graph tends towards positive or negative infinity as the input approaches a. So it means as x approaches that number, f of x is going to infinity, or as x approaches a number, f of x is going to negative infinity. So if you look up here in this picture, you can see that there appears to be this like imaginary boundary that's going on of a vertical asymptote. This has the equation of x equals to 0. And then what you can do is, you can see from our notation, and what we'll have to write as notation, is as x approaches 0 from the left, so we can see as the graph is approaching 0, coming from the left, it looks like it's going downward into kind of infinity, so we would say f of x approaches negative infinity. Other observations we can see as x approaches 0 from the right, again, that's our new notation. So as our graph is being read, as it gets closer and closer to 0, it looks like it's going up and up into positive infinity. So we're looking at f of x to positive infinity. There will be some problems on your assignments, and they'll give you the first part, and they're wanting you to fill in the second part. So I just want to kind of emphasize what this notation means, how it can be read, and this brings in that aspect of vertical asymptote. The other new word is your horizontal asymptote, and it is a horizontal line, y equal to b, again, that's the equation of that line, where the graph approaches the line as the input increases or decreases without bound. So nothing new looking at our end behavior as x approaches infinity or x approaches negative infinity. Instead of looking at the end behavior going to infinities like we did in previous sections, it's now approaching some kind of value. Again, previous example here, there's like this imaginary boundary line that looks like it will never touch it. And we can see as x is going off to positive infinity, it looks like it's getting closer and closer and closer to 0, but it's never going to get there. As it's going off to negative infinity, we can see that this function is getting closer and closer in 0, but never going to get there, which makes sense because f of x is equal to 1 over x, and we can never have that to be 0. So it's going to get real close to it, but it's never going to actually reach that value of 0. So this will be the two main concepts that we're looking at in this section. How can we find vertical and horizontal asymptotes? How can we interpret them? And how can we see them from graphs or equations? So first example here, it says use arrow notation to describe the end behavior and local behavior of the function below. So first thing I want to emphasize is let's look at the asymptotes. You can see that I already have it drawn here. So this is your vertical asymptote, and it would be at the equation x equals to 2. Then here you can see we have a horizontal asymptote. And the horizontal asymptote here is at y equal to 4. And these are the equation of the horizontal and vertical lines. Now let's just added information. We want to now use our arrow notation to describe the end behavior and the local behavior. Well, let's look at the end behavior first. As x is going to positive infinity, so as our x is bigger, you can see it's approaching this value of 4. So we would say f of x is approaching 4. Notice I'm not saying equal to 4, I'm saying it's approaching 4. As x is going to negative infinity, so as it's getting further and further and further out here, you can see it's also approaching 4. Again, not new with our end behavior. We've looked at that before when we did kind of our lead coefficient test. Now, newer notation, let's look at our local behavior. What is happening as x is approaching this vertical asymptote at 2 from the left? And what is x doing as it approaches 2 from the right? And we're going to have to look at what the graph is or the function is doing. So I'm going to say, what is it doing as it's approaching 2 coming from the right? Coming from the right, it looks like it's going up to positive infinity, so we say infinity. As it's approaching 2 from the left, it looks like it's dropping down, so it's approaching negative infinity. This information would probably be given, and then the f of x version is what's going to be needed to be answered within the question. Now, looking at a graph, I hope you start to understand how you can pull that information from it. But furthermore, we're not always given a graph, and we don't use graphing calculators on an exam. And so it's important for us to be able to note, how can we identify these asymptotes? How can we identify different characteristics from just looking at the equation? So that leads us into part 2. Let's look at the domain of these functions. Now, our conversation of domain is just a continued conversation. We looked at domain and range in earlier chapters and units, and we even talked about domain and range of these parent functions that we started out this section with. If you go back into about 1718, we talked about all the different domain and ranges issues. Now, when we're looking at the domain of a rational function includes all real numbers except those that cause the denominator to equal 0. And we've talked about that in other lessons, because if we have 0 in the denominator, that means we have division by 0, which is undefined. Our calculator cannot even do it. So if we're looking at the domain of one of these rational functions, a function that's been written as a fraction, we're going to take our bottom, our denominator, and set it equal to 0. Then we're going to solve it out. So we're still solving those quadratics. So in order to get x by itself, I square root. I'm going to get x to be, don't forget, plus or minus 3. So what is the domain of this function? It's all real numbers except x equal to negative 3 and 3. And some of the problems already have them set up for you, and they just have you entering these last ones. So we're looking for problem areas in our function. We've talked about that before, and it's looking where you have division by 0, square roots of negatives, etc. Let's look at this other problem. It says find the domain of f of x. Now with this problem, I specifically want to work this one because same approach, you're going to set the bottom equal to 0 and solve. But don't overwork this problem. Don't FOIL, distribute this all back together, and then try and factor it out from there. It's already factored in the form, so if I have something times something times something to give me 0, that means one of them had to be 0. 5 can never be 0. X minus 1 could be 0. So that gives me x to be 1. X minus 5 could be 0. So that gives me x to be 5. So I would say, what is the domain of this function? All real numbers except x equal to 1 and 5. And so I specifically wanted to work this problem here because I wanted to emphasize, don't overwork the problem. Don't go back and put something together that's already factored. And there's a time and place for us to factor it back out, and we'll get to that. So we have this idea of domain. So let's take it further and put that together with our vertical asymptotes conversation. And so you can see we have a how-to. How to, given a rational function, identify any vertical asymptotes of its graph. Well, 1, you're going to factor the numerator and denominator. You're going to factor it out into all its pieces. 2, note any restrictions in the domain of the function. 3, reduce the expression by canceling common factors. 4, note any values that cause the denominator to be 0. These are where the vertical asymptotes occur. And note any restriction where asymptotes do not occur. These are removable discontinuities, which See next page. We're going to look at that here in a minute. So in this first one, find the vertical asymptotes of the graph. So what we're going to do is we're going to take the function, we're going to factor it out as much as we can. Now the top piece doesn't really factor out, but in the bottom piece we have, I'm going to rewrite them in order by descending exponent. And then I can factor out -1. So that gives me x squared plus x minus 2. And the whole reason I did that is it makes it really nice when I go to factor this that I have my two parentheses. So I think what'll factor to give me, what'll factor to give me x squared, that's x and x. Let's see, my back sign is negative, so plus and minus. What will multiply to give me -2 and add to give me +1, that's +2 and -1. So again, still got to know your factoring skills. So if I set my bottom equal to 0 now and solve, I could say, well, -1 is never going to be 0, but x plus 2 could be 0 and x minus 1 could be 0. So that gives me -2 and 1. So this is where I have vertical asymptotes. And it wasn't a matter of looking at my graph and finding them. It was a matter of looking at my denominator, factoring, and solving. So sadly, you still have all those factoring skills that we've been doing since Unit 1. So I would have vertical asymptotes and -2 and 1. And again, these are equation of vertical lines. Now let's dive a little bit deeper with this new vocabulary of removable discontinuities. In removable discontinuities, it says, for example, the function. I thought a really nice example and equation would help with this. So say we had this equation here, x squared minus 1 all over x squared minus 2x minus 3. We could rewrite it by factoring the numerator and the denominator. So in the top, that's the difference of two squares, so x plus 1, x minus 1. In the bottom, we factor it like the previous problem, x plus 1 and x minus 3. Notice that x plus 1 is a common factor to the numerator and denominator, so I can actually cancel those out since I have it broken down in factors. And because I can cancel it and remove it, this is a removable discontinuity. Now the pieces that remain, whatever you have left in the bottom you could not cancel out, is your vertical asymptotes. So I'm just going to abbreviate that. Pictorially, you can see this removable discontinuity doesn't create an asymptote, a big boundary. It just creates an open dot because I'm never going to be able to plug -1 in and not get division by 0 like I saw in the problem. But everything else up to it does work. Now with the x minus 3, that created a vertical asymptote here. So you can see our reciprocal function has been shifted and has a vertical asymptote at that x to be 3. So applying this all together, let's just kind of look at this problem here. So the first thing you're going to do, it says find the vertical asymptotes and removable discontinuities of this graph. So you're going to take this function and you're going to factor it. So this is the difference of two squares. This factors into x plus 2 and x minus 2. And if you need more assistance with factoring, just shoot me a Canvas message. I'll be happy to send you more resources and helps along with the way with that. Now you'll notice these x minus 2's cancel. So since they were removable, I can say x minus 2 equal to 0, x equals 2. That is a removable discontinuity. The only one that remains in the bottom I can set equal to 0 and solve. And that is the equation of my vertical asymptote. So you can see your factoring skills are coming into play. This conversation of vertical asymptotes we're now applying with equations. You're going to see similar format of your problems as you move into the homework. So definitely use the notes to help you with the homework and use me as a resource. If you have any questions along the way, just shoot me a message. So last problem, I just want to put it all together and I want to kind of see how we can apply this. So let's kind of put it together and see how we can apply this. So it says the concentration C of a drug in a patient's bloodstream T hours after injection is given by, and there's my function, and that's a rational function. That's the whole reason you'll see it in this section. And it says, what is the concentration of the drug after 2.5 hours? So it's saying 2.5 is my T, and so I'm going to use that T value just to kind of plug and chug through this. So I'm going to say 40 times 2.5 over 42 plus 2.5 squared. I'm just going to use my calculator as I go. I want to make sure that I did 40 times 2.5 40 times 2.5 gives me 100. Just type into my calculator here. And then 40 plus 2.5 squared gives me 48.25. And so when I divide that out in my calculator, I get 2.07. It did say round to 2 decimal places, and so that's my concentration after 2.5 hours, because that was my T. So part A, that's evaluating a polynomial. That is like day 1 of college algebra. Next part says, how long does this drug stay in someone's bloodstream? Assume that the drug is out of the patient's system once the concentration has decreased to 0.6%. Round to 2 decimal places. So that means I'm probably going to have to use my calculator. It's not going to work out to nice 2s and 4s. And so notice that's my concentration. That's what it's equal to. So I'm going to say 0.6 is equal to 40T over 42.T squared. And I'm going to solve for this. Well, I don't want to deal with this fraction over here. I need to get the t's by themselves. So I'm going to multiply both sides by 42 plus t squared. That would eliminate it being in the denominator, but just move it to the other side of the equation. And then I'm going to distribute that 0.6. So 0.6 times 42 gives me 25.2 plus 0.6 times t squared equal to 40t. So right there, we're back at unit 1 solving a quadratic. So I'm going to bring the 40t to the other side, because whenever you're solving a quadratic, you want it in standard form, everything lined up, and set equal to 0. Now this thing I'm going to tell you, I've tried to factor it, doesn't factor. It does say round to 2 decimal places, and so that means you're going to have to use your quadratic formula. So that's going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. So your A is 0.6, your B is negative 40, and your C is 25.2. So I'm going to finish this out. This tells me negative B plus or minus the square root of B squared minus 4 times A times C all over, kind of ran out of room there, 2A. So it's 40 plus, only plug in what's underneath your square root in your calculator. So that is the square root of 1539.52, because I don't want to round this at any point until I get to my final answer. All over 1.2. So in your calculator, you want to type in 40 plus the square root of that, enter, divide it by 1.2. That gives you 66.03. 40 minus the square root of that, divide it by 1.2, and you get 0.64. But since this problem said that after 2.5 hours, it's at a 2% concentration, after all this, getting a 6% concentrate, 0.6% concentration after half an hour, that doesn't make any sense. So this is the only answer, because remember, this is our t value. So that means after 66 hours, so it takes a while for this drug to get out of their system, we would have it down to 0.6%. Now it says, what is the end behavior of the function? Like, what's going on as our time gets larger and larger and larger without bounds? Well, our concentration is not going to get higher. We've already seen as our concentration goes down is what's happening. It's also not going to be a negative value. I mean, we're in the real world. Like the blood concentration of this, the patient's, the drug in their blood. And these answers don't even make sense. Like, as I live on, I'm going to have a 40% concentration in my life. I'm going to have that in my bloodstream. These don't make sense. So this is the only one that makes sense for this application of it. So we're kind of taking our conversation of end behavior and putting it together with our conversation of application. So I hope this helps with this section. If you have any questions along the way, feel free to message me. I'll be happy to help you out. But definitely use this as you do your homework. This problem specifically, you have exactly in your homework.